All right. Hello again, Ling statisticians. It is time for another homework. I'm sure you're all as excited as I am. This one is going to be about Anovas, and it's due on Friday the 26th. Today it's already the 20th of November. It's Saturday, so you have just a few days to work on this, which is why I want to get this up as soon as possible. So with no further ado, there are three problems in this homework. They all ask you to run Anovas. The first one goes back to the baseball data, except it's a different baseball data set than what we saw before. So I'll explain to you what differs here. This data frame includes the same numbers that we've discussed in class: batting bases produced, plate appearances, and batting base production average. So these are the plate appearances here. There's also batting bases produced. How many bases does the offensive team reach on those plate appearances, and then the average, which is basically this number divided by that number. So that one's going to be like 0.35. Okay, what differs here from what we've seen before is that the team data this is data broken down by team in the major leagues for the 2010 season, like the Arizona Diamondbacks or the Boston Red Sox, so on and so forth. And we have these same fields of batter and pitcher that we saw before, but there's a new twist because each batter column includes the switch hitters on each team. So before we just had right-handed hitters and left-handed hitters and right-handed pitchers and left-handed pitchers. Now we have switch hitters, which are represented with a B, and those are hitters that hit with both hands. So switch hitters are batters who try to take advantage of the handedness matchup pattern that we previously observed in class. They bat right-handed against left-handed pitchers and bat left-handed against right-handed pitchers in the hopes that this will improve their batting performance overall, right? So when you have different handednesses of batter and pitcher, it's supposed to give a bonus to the offense. These are guys who, let's say they are, natively right-handed. They teach themselves how to hit left-handed as well as right-handed so they can switch back and forth depending on who is pitching against them. I will also note that there are two teams, namely the Toronto Blue Jays of all teams and the Cincinnati Reds, that didn't have any switch hitters back in 2010, so their data is not included here. That means we have 28 teams, whereas before we had 30 teams in the entire data frame. But for just this data, just focus on what we have in this data set right here. Run an Anova in which you investigate the effect of batter handedness, pitcher handedness, and their interaction on batting base production average. So it's going to look a lot like what you did before, or what we all did before in the lecture notes, but we have three different levels in the batter factor now rather than two. So report the results of the analysis of variance for the two independent factors, batter and pitcher, and also their interaction. Which factors' interactions are significant and which are not. Once you figure out what the significant effects are, run post hoc tests to determine the direction of significance for each significant result you get. And what I mean by direction is, well, if you get an effect of batter, like are the right-handed batters doing better than the left-hand batters or vice versa, just tell me which group has the higher overall mean than the others. You can figure that out based on the post hoc tests that you run. And when you do run those post hoc tests, you should be applying one of those alpha corrections we talked about in lecture. So please specify which one you used. Yeah, that should hopefully be straightforward. And if you have any questions about that, you can go back to that lecture. It's all laid out in painstaking detail. And then lastly, once you figure out the direction of significance for the significant factors, you should answer the questions. This question of, is the strategy of switch hitting successful or not for those batters who use it? Remember, you always got to kind of tie this back up to the research question overall. And this is our research question here in this particular case. Even though it's about baseball, not linguistics, the same principles apply for the stats you run. Okay, hopefully that makes sense. That's problem number one. Problem number two, we're also going to go back to data we've seen before. So in this case, we are going to go back to the sensitivity and bias data we calculated for homework number 7, which I'm sure you all remember and all still love because that's one where we did all that scripting. In this case, you don't have to generate any of the data again because I've done it for you, and I've tweaked it a little bit. So this is giving you just a data frame where we have, say, the different listeners. That's our first column. The stimulus type that they're listening to, whether that stimulus type includes that prosody switch, or rather the syllable duration switch between one stimulus type and another. 0 means there hasn't been a switch. 1 means that there has been a switch. And then for each individual subject, we get a D prime measure for those stimuli, and then also a beta measure for those stimuli, in this case, ADS no switch. Right, so I've generated those for you here, so you don't have to go through that part of the process again. But also please note that in this data frame, I've eliminated 2 subjects from the data you looked at before. So now there is an equal number of subjects in both the switch and no switch listening conditions, and there's 18 overall in these groups. So what I want you to do is to run 2 two-way Anovas, one in which you investigate the effects of stimulus type, IDS or ADS, and duration switch, switch and no switch, on the values of D prime in this data frame. So stimulus type is the column here, ADS or IDS, and then switch is either no switch, which is 0, or switch, which is 1, right? So hopefully this stuff should sound pretty familiar. The first Anova, your dependent measure is going to be D prime, the sensitivity measure, and your second Anova is going to be the values of beta or bias in this particular case. So they're clearly labeled there. Report any significant main effects or interactions that you find, and then run post hoc tests to determine the direction of significance for each significant effect. Again, apply a relevant correction to the results of your post hoc tests and let me know which correction you used. And generally speaking, as always, when you find a significant effect in these post hoc tests, tell me, which number is bigger than the other. So you kind of complete the story that way. And also, if you're lucky enough to be in Ling 660, tell me a little bit more about the overall story we've been thinking about with respect to this data. So does the story of how these 2 factors influence the listener's performance on the syntactic disambiguation task change once you have the results of these Anovas rather than just a series of t-tests? And if so, how? So you're going to have to do a little bit of thinking about that. But again, if you have any questions, you can always ask me in office hours or by email. Problem number 3 is a new set of data. I used to talk about this in the lecture, but I got rid of it. It's a cool set of data, though, so I'm happy to talk about it. It's some data that one of my former students, Sue Jackson, collected a while back for an Abx discrimination experiment that involved 2 groups of listeners, native English listeners and native Hindi listeners. So this data is here. There's a lot of fields in it. So there's a fair amount to worry about in it, but where does it all come from? What this is showing you is the results of this discrimination experiment where listeners were discriminating spliced together combinations of cues to different phonation contrasts. So in English, we have in onset position typically an unaspirated versus aspirated contrast for stops. So B, which looks like a voice stop, is really just unaspirated. P, which is represented with a voiceless stop symbol, is aspirated. So that's unaspirated versus aspirated. In Hindi, there is a 4-way contrast between voiced unaspirated and voiced aspirated, and then also voiceless unaspirated and voiceless aspirated. And then sometimes the voiced aspirated stops can have breathy voiced aspiration as opposed to just regular voiceless aspiration. So Sue is interested in looking at whether your native language will affect how you process these little cues to different phonation contrasts, whether you categorize a stop as voiced or voiceless or aspirated or unaspirated, that sort of thing. So she didn't really use those categories, but what she did is that she had listeners hear 2 stimuli with the same amount of stop closure voicing, long, short, or none. So she also kind of split up closure voicing into 2 different categories there, long versus short. And then, there's like a ba with a long amount of voicing, and then another ba with a long amount of voicing. But those first 2 stimuli differed in their types of aspiration. So was the aspiration that followed that closure voicing, or what have you, was it breathy voiced, or maybe it was voiceless aspiration, which is how we normally think of it, and then also maybe not aspirated at all. The task of the listeners was to determine whether a third stimulus, X, was the same as the first, A, or the second, B, stimulus they heard on each trial. So that's Abx discrimination. You hear 3 sounds. You decide whether X is the same as B, the second one, or A, the first one. Okay, so the only way these stimuli are differing within each trial is in the form of aspiration that they have. So, for instance, this first trial, we have subject number 1, whose native language is English. This person is hearing long voicing in the closure phase of these stops. And in the first trial, they hear an unaspirated stop. In the second B trial, or second B stimulus, they hear a breathy voiced aspiration. And then the X stimulus, they hear breathy voiced aspiration. So they have to link up X with B in this particular case. Okay, apologies for the interruption. Anyways, where we were, I've made this a little bit bigger because I watched the end of the last snippet. So in this first trial, the X is kind of equal to the B stimulus here. So the other, the other parts of this that you need to consider are the place of articulation is the next field, which actually kind of is not going to matter for our analysis, but it's either velar or retroflex, because these were made in, these are Hindi stops originally, so we don't have retroflex stops in English so much, at least not phonemically. But don't worry about that for now. The part of this which kind of gets interesting is that this is the target, this is what they're supposed to respond with, and this is what they actually respond with. And then this is whether or not they're correct, 0 for incorrect and 1 for correct. What we're going to focus on in this particular exercise is the response time. So this is measured in milliseconds. So 1,446 milliseconds is 1.446 seconds, or this one here is 2.477 seconds. So, if it takes a subject longer to make a decision about what they've heard, normally that isn't taken to be indicative of a greater amount of confusion about what they've heard because they can't figure it out as easily. And if they have faster response times, like 851 milliseconds, it's an easy decision for them to make. This label here tells you what contrast was being tested in this particular trial. So BU just means that we're comparing breathy voiced aspiration with unaspirated stops. And then there's other comparisons like HB. H is aspiration and B is breathy voiced aspiration, so on and so forth, like down here. The context is just how much voicing there was in the stop itself. So L for a lot of voicing, N for no voicing, and S for short amount of voicing. So kind of the part that matters is at the end here. And so what I want you to do after having walked through all of this is to, number one, run a repeated measures Anova for Sue's RT data. So you're going to wind up getting more than one repetition of these individual pairings of aspiration types. So you're going to get them across different places of articulation, and then you wind up getting them actually a couple of times for each pairing. So here's the LU and LB combo again with a different sort of X comparison there at the end as well. So run a repeated measures Anova for the RT data. And what I want you to do is consider the influence of the following factors on reaction time. So this is your dependent measure, is that RT in the data frame. So look at the language of the listener, which is here. So there's English at the top of this, and there's a lot of data in here, and there's Hindi at the bottom. And then look at contrast type, which is this variable here, the BU and the HB in this field, so on and so forth. Also look at context, which is how much voicing there was in the stop itself, and then also their potential interactions. So this is tricky because it's a three-way Anova, and so that can give you a lot of complex results, potentially. And I think I recommended you never should do more than a three-way Anova, so we're just going to limit it at that, even though there are other factors here that are of interest that we could look at. So just a heads up, if you wind up with a lot of significant effects when you run this repeated measures Anova, then something's gone wrong with the R command you used, which is easy to do with a repeated measures Anova. So in that case, find the error, fix it, and run it again. The significant results you should get out of this should be relatively small and manageable. Once you find out what they are, report the relevant statistics for all the significant results, but don't run any post hoc tests yet on this data set, because what I want you to do is take another step, or actually two other steps. that researchers often do to filter their data with reaction time studies. So this is part B. So number one, when people look at reaction time, first of all, they don't analyze any incorrect responses. And the reason they do that is because the cognitive process leading to an incorrect response is likely to be significantly different and also take a meaningfully different time course than a correct response to a stimulus. So there's a bit of variance in there, which kind of leads to different pathways in your mind, which means you can't really compare those or group them together in a meaningful way. And so the way you can kind of filter those out, there's this correct field in the data set. So as you can see, there's a fair number of incorrect responses here because this is not an easy task. But I want you to look at the correct responses, which are labeled with a 1 here on each trial, which means that we're getting a match between these two fields. Okay, number 2, what people will do is eliminate outliers, which are more than 2 standard deviations away from the mean response time. So yeah, I don't know if you've ever run a reaction time study in your life. Here's an interesting example. So a lot of these response times are around a second or maybe up to 2 seconds, maybe somewhat less than a second. That's like a fair amount of time for a person to take to respond to the stimuli, to be able to process it and actually give a meaningful response. Sometimes you might get people who just like blah, 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 blah. They don't really care what they're hearing. They're just clicking the button as fast as they can to get out of there. In that case, you might expect a lot of super short response times, like 60 milliseconds, which are like, that's faster than a human being can process this information. Or you might get a super long one, like 62,000 milliseconds, that sort of thing. So, we've talked about outliers in this class before. This is kind of a standard approach that people use to eliminate outliers. It's not really a principled approach, which makes it a little bit problematic. I'm kind of having you do this almost as a pro forma exercise so that you know how this process works. And you'll know what it looks like when other people do it. But the idea here is that you just calculate 2 standard deviations away from the mean. So just like a really, really long or really short response time, and you get rid of those just under the assumption that if they took that long, that they probably weren't engaged meaningfully in that particular trial. And when you do that, you have to sort of calculate the standard deviation and mean with respect to only the correct responses, because again, they are alike in a way that the incorrect responses are not like, or whatever you would say in that case. So separate out the incorrect stuff, do that first, and then eliminate outliers from the correct responses only. Filter SUSE RT data in these 2 ways, and then rerun the repeated measures ANOVA you ran for part A. And then let me know, does this change the results of the ANOVA in any way? So let me know what that is. And then also run another set of post hoc tests for the significant results, and actually run a set of post hoc tests for the significant results and report the results of those tests. So in this case, actually do the follow-up analysis and tell me what you get. And I'm going to mention here, there are some of these assumptions of the repeated measures ANOVA, which are supposed to be satisfied, right, in order for this to be meaningful. And one way that you can kind of help yourself out if you can't satisfy these assumptions is to make sure the number of observations in each factor level is balanced. But I will let you know in this case, if you filter out the incorrect responses, like these start out as balanced observations across the different groups or pairings of stimulus factors. But once you filter out the incorrect ones, that's no longer necessarily going to be the case. So we might be violating some of these assumptions with this exercise. But as I say on this, and including you might violate the sphericity assumption as well. I'm going to say if you acknowledge that, that's fine. But this is more complicated than we need to do for right now. So I'm going to say sort of statistically sinfully, just ignore this at the moment. You might be doing the totally wrong thing here. Just answer these questions with the results you get from the ANOVA and the post hoc tests that you apply to this data. And I'm also going to say, once again, if you get a lot of significant results for this particular ANOVA in part B, something has once again gone wrong with your R commands. Hopefully they shouldn't be too overwhelming. So double check your work and try it again and get something that's manageable at the end of the day. This is not a problem that I want to put out there to, break your mind or something like that. I just want you to kind of get a sense of how this approach works for real language data or data you might collect yourself in a linguistics-based speech perception experiment. Okay, so after finishing your work for both problems, send me your answers to each question and your saved R console via the Dropbox on D2L, and let me know if you have any questions. Hopefully this all makes sense, even though it looks like a lot. It should be manageable for you to get done by this Friday. So I'll be looking forward to what you have for me by then. Okay,